Lesson 1.4, working with radicals. This lesson is going to be critical for you to remember as you move forward in all of the math that you do from here on out. You're going to learn all of the rules, all of the tricks when working with radicals. Okay, Mr. V, what's a radical? Well, we'll get to it in a second. First, I'd like to challenge you by this little Venn diagram of types of numbers. So we've got whole numbers, rational numbers, integers, natural numbers, real numbers, irrational numbers, and some of these groups fall inside of other groups. Some of these sets are subsets of other numbers. And so I want to see if you can just take a pencil out and see if you can place the words within the correct spot in the Venn diagram. And I'll give you a hint. All of the numbers here are real numbers. Okay, so there's a set of real numbers here that doesn't relate in any way to the set of real numbers here, but these guys all are kind of inside of each other. Pause the video, take a second, figure it out, see how you do. All right. I don't really have enough space to give you examples for all of the different number groups. Probably should have done that. But at any rate, the smallest set of numbers are the natural numbers. Natural numbers are the ones we count with. 1, 2, 3, 4, 5, 6. They're whole numbers and they're positive numbers. Now, if you add one more number to the list of natural numbers, you get all of the whole numbers, which is all of the natural numbers and 0. So now we have 0, 1, 2, 3, 4, 5, 6, etc. The next step includes all of the negative numbers, which is then all of the integers. This is positive and negative whole numbers, including 0. Okay? And then beyond that, we get the rational numbers. Now, if we just think about this for a second, we've got a number line. 1, 2, 3, 4, dot, 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 keeps going. -1, -2, -3, keeps going. We've got the natural numbers right here. Whole numbers right here. Integers, going on and on. These guys go on forever this way. And then we're talking about the rational numbers. Well, the rational numbers basically means that any number that can be represented by a fraction. Okay? So that means within even, let's just take from 1 to 2. Well, there's actually an infinite number of numbers inside the space between 1 and 2. Like 3/2. Okay, that's a rational number. It's 1.5. It can be represented by a fraction. But there are so many more, okay? Any number that is greater than 1, but still less than 2, like say 7/4. That's a rational number. Falls between 1 and 2, can be represented as a fraction. Which means that over here we have the irrational numbers. These are numbers that cannot be expressed using fractions, okay? We're going to talk about what those are. So they can't be expressed in terms of a fraction, a over b. And one type of number that makes its way into here is radicals, okay? A radical is basically the square root of a number, but it's the square root of a number that can't be reduced, that isn't a square itself. So for instance, the square root of 25 is not an irrational number. It's represented as a radical, but it can reduce to 5, okay? Which falls into this category over here. At any rate, today we're going to be learning about radicals. The rest of the space underneath the Venn diagram is going to be taken up with some notes about radicals. This is a radical, okay? The whole thing is a radical. It's the square root of a number. The value that is under the square root symbol is called the radicand. Okay? Now, if the radicand is not a square number, That means it's not 1 or 4 or 9 or 16 or 25 or 36 or 49, on and on, and it's not 0, then this is an irrational, the radical is an irrational number. Now we could find an approximate value for this radical by just checking it in our calculator. But what you'll get is a string of decimals, and it will be rounded, okay? Because in reality, the string of decimals goes on forever and ever and ever. So if you round it to, say, 2 decimals or 1 decimal or 8 decimals, you're not getting an exact answer. You're getting an approximate value. So what we actually want to do in order to be accurate in our math and in our science is to use the radical itself to get a very accurate answer, to get an exact answer, which means we need to know how to work with radicals without converting them into decimals, okay? Now, the whole thing is a radical. The thing underneath is called a radicand. And the only other thing that we need to know from here is a mixed radical. A mixed radical, sometimes you can take this radical, or it's in a math problem with other things, and you can create a mixed radical. I'm just going to change color marker here. A mixed radical has 2 parts. It has a constant factor, and it's a times the square root of b, or a times radical b. Okay, in this case, a can't be 1, wouldn't make sense. Anything times 1 is just itself. It can't be -1, and it has to be, and b has to be greater than 0. Here also n has to be greater than 0. There's no such thing as a negative radical. You can't take the square root of a negative number because there's no such thing as a value times itself that would equal a negative number. Okay, if A is positive, then positive times positive is positive. And if A is negative, then a negative times a negative is a positive. So this guy, this value, the radicand, can never be negative, okay? An example of this, so this is called a mixed radical. And an example of that would just be something like 3 radical 5, or 2 radical 7, okay? So just one more note to add then. N is always greater than 0. And here, B is always greater than 0. And A can't be 1 or -1. All right, example 1, we're given 3 different radicals, and we're going to express them in simplest form. Now, one of the tools that you're going to need here that isn't given yet, it was in an investigation that we skipped, but it is the idea that a radical can be split into its factors. So, for instance, if we have, let me just write it. If you have a number, and it can be represented as a times b, that's actually equal to the radical of a times the radical of b. Okay, you could test that out a whole bunch of different ways. You could test it out in your calculator. You could do 12 times 9 and take the square root of that. And then you could take the square root of 12 times the square root of 9. And you'll notice that you get the exact same answer. Okay, so that is one of the properties of radicals that we're going to use all the time. So basically what we're going to do is we're going to look at this radicand. That's the value under the square root symbol. And we're going to see, can this thing be split into factors? Yes, it can. But we're only going to choose the factors that are helpful to us in reducing to simplest terms. What does that mean? We actually want to pull out a factor that is a square number. Okay, so if I look at this thing just off to the side, I could say, well, the factors of 50 are, 1 and 50. It's already in that, so that doesn't help me. 2 and 25, we'll talk about that in a second. 5 and 10, and that's it. So my options here are to split it into 2 times 25 or 5 times 10. Some of you are seeing right away, okay, a square number. Okay, splitting it into 5 times 10 doesn't help me. I'm just going to get radical 5 times radical 10. But if I split it into radical 2 times radical 25, I can reduce radical 25 to 5 and carry on from there. Okay, so this is what it looks like. We're going to take the radical 50, I'm going to leave it under a long radical sign, and I'm going to split 50 into two factors. I'm going to use 25 times 2, still equals 50. Now, because of the property that we talked about before, I can now simplify this further, and I can split it up into two pieces. I can say the square root of 25 times the square root of 2. Now, I can't simplify the square root of 2 any further. It's just going to be left as a radical, but the square root of 25 is 5. Default operation of algebra is multiplication. This reduces to 5 radical 2, or 5 times the square root of 2. Let's go over here to 27. 27 is actually 9 times 3. Well, 9 is a square number, so that's really helpful. Under the radical sign, I've got 9 times 3. Again, I'm doing every step, but at some point, you can get good enough to skip these steps. That's radical 9 times radical 3. Well, radical 9 is 3, so now I have 3 radical 3. A really big temptation here is to say, oh, here's a couple. This is 3 cubed, so why can't I work with cube numbers? Well, you're not dealing with cubes, you're dealing with square roots and square numbers, okay? That's one reason. The other thing that gets tempting is to kind of forget about the other part, to forget about the radical 3, or to say, oh, this is 3 times 3. No, it's not. Okay, or, oh, this is 9 radical 3. No, it's not. Square root of 9 is 3. Radical 3 is reduced as far as it can be. So just be careful, be patient, take your time. And it's a bit of a logic problem, really. Now, this one, you can do a couple different ways. But 180 is divisible by a couple of numbers. One of those numbers is the number 36. So what I would do is I'd kind of just go into my factors. I'd say, okay, this is 1 times 180, or 2 times 90. That doesn't help. Or 3 times 60. That doesn't really help, although maybe I could split 60 up into square numbers. Let's keep going. 4 times, I could divide it by 4 and get 45. That could be helpful because actually 9 is a factor of 45. So that would give me 2 squares. We'll work with that one next. But the easiest one here, I think, is 5 times 36. And again, you can use your calculator to check for factors. Just 180 divided by 2, 180 divided by 3, 180 divided by 4, until you get a square number that you recognize and can work with. So we recognize that this is going to be 36 times 5. You can split that into the product of two radicals. It's radical 36 times radical 5. Radical 36 is 6, and radical 5 is reduced as much as possible. Now, we also said, I'm just going to rewrite the problem here, and if you have space, you should do this, just to show you can do it two different ways. So we said that it would be 4 times 45, and I can actually split 45 into 4 times 9 times 5, okay? 45 is 9 times 5, and 4, I'll just split it into its pieces. You'll be able to see it really clearly. 4 is a square number and 9 is a square number. So I've got 2 times 3 times radical 5, which is 6 radical 5. Okay, yeah, it took an extra step, but we were dealing with smaller numbers, and maybe this is easier for you to see, and you know, you really don't even need all of the steps. If your brain can go straight from, let's say, here to here or here to here, and you're skipping some steps along the way, that's okay. But just make sure you show enough work that you can understand how you got to where you're going, and that I can understand how you got to where you're going, especially if you get the wrong answer, and I need to find a way to give you some points. In example 2, we deal with adding and subtracting radicals. Now this works in the same way as adding and subtracting polynomials. You can only add and subtract like terms. So when dealing with polynomials, if you've got some x squareds and you've got some x's, you can't add the x squareds and the x's together. They are not the same. But if you had another 7x and 2x, you could add those. They would be 9x. Those are like terms, okay? Radicals work in the same way. So you can only add values that have the same radical. For instance, if you have 5 radical 3's and you have 2 radical 2's, you cannot add those up. It's not 7 radical 3's or 7 radical 6's or 7 radical 5's or anything crazy like that. But if you had 2 radical 2's and 4 radical 2's, you could add those up. You've got 6 radical 2's, 6 radical 2, okay? So let's take a little note on that and say it works just like adding terms in a polynomial. You can only add terms with like radicals. That's just an interesting way of saying they gotta have the same radical, okay? You have to have a common radical in order to add. If there's no common radical, you cannot simplify any further. Well, let's go ahead and look at the things that we need to simplify in example 2. We've got a is 9 radical 7 minus 3 radical 7. Well, that's not that difficult. If you have radical 7's and you've got 9 of them here and you're going to take away 3 of them, what does that leave you with? It leaves you with 6 radical 7. Okay? All right, we're looking at B. B says 4 radical 3 minus 2 radical 27. Now you might look at this one and say, oh, different radicals, can't add them, but think back. Look at this bigger radical here, this radicand of 27. It's actually divisible by 9, which is a square number. And if I do that, I am going to get 9 times 3, which is going to leave me with a radical 3 on both sides. So let's work that out and see what we get here. First term I can't change. It's 4 radical 3. That's as simple as it's going to get. Over here I've got 2 times radical 9 times radical 3. Okay? Notice I'm starting to skip steps as we go. 4 radical 3. I'll do this in 2 more steps. 2 times radical 9 is 3 times radical 3. Leaves me with 4 radical 3 minus 6 radical 3, which is negative 2 times radical 3. Yes, you can go into the negatives when you're adding and subtracting, even when you're adding and subtracting radicals. The next example looks like nothing really in common, but actually both of these radicals can be simplified. So we're going to do that really quickly. I'm going to start skipping more steps so we can move along. But radical 8 is radical 4 times radical 2. And radical 4 is, well, maybe I'll just do that first. Radical 4, radical 2. And on this side, this is radical 9 radical 2. So I am going to have a like radical. Well, square root of 4 is 2. 2 times 5 is 10. Here I have 10 radical 2. Square root of 9 is 3. 3 times 3 is 9. So here I have 9 radical 2. I'm adding these guys up, so I have 19 radical 2. Example 2D is one of those, oh, why would they do this to me type questions. But we're just going to work through it simply, peacefully, step by step, see if we can find some square values. Okay, so I'm going to start over here. It gives me a little bit more space to work down. And again, I'm just going to look at each term. I'm not going to deal with the fraction at first, but I am going to deal with the radicand. And I can see, remember, I want to create square numbers. 28 is 4 times 7. Okay, so I'm going to go ahead and write it right away as radical 4 times radical 7. Subtracting 3/4 of our next piece. 63 is 9 times 7. So that's going to be radical 9, radical 7. I see my common radical already. And then I'm going to add 2/3 It'd be great if I could make this into a radical 7, but I can't. It's 25 times 2. We dealt with that one already. So radical 25 times radical 2. Okay, I'm going to just make this into a multiple and then show you the next step from there. Okay, so this is 1/4 times square root of 4 is 2 times radical 7. This is 3/4 times 3 radical 7. And our next piece is 2/3 times 5 radical 2. Okay? I can see, because I know that multiplication is the default operation in algebra, and that multiplication, when I'm solving something, needs to be done before addition and subtraction, that I've got 3 chunks here still. Okay? Hopefully you can see that as well. Now is not the time to start, adding your quarters and your fourths and your thirds together. That's not going to be helpful at this point. You still need to deal with the multiplication that's involved here. Another thing to note is that it's easier to see here, but this is all multiplication, right? Multiplication here, multiplication here. That means the radical 7 is just as attached to the 1/4 as it is to the radical 4. Okay? Even though it was like this originally and the radical 28 was together, you could just as easily write this 1/4 times radical 7 times radical 4. Or, for instance, here, it says 2 radical 7. But this 2 is just as connected to the 1/4 as it is to the radical 7. It's multiplication here, it's multiplication here. So that means I can write this as 2/4. 1/4 times 2 is 2/4. 2/4 reduced is 1/2. But I'm going to leave it as fourths because I have some fourths here. And I have a feeling I'm going to be able to combine these guys using my fourths and using my radical 7. So I'm actually going to leave this as fourths. This is going to be 2/4 radical 7. Subtracting. Now I have 3/4 times 3. That's 9/4. 9/4 times radical 7. And over here I have 10/3 plus 10/3 times radical 2. All right. Now what do I have? I have 2 terms that have a like radical, and they also conveniently have the same denominator as their multiplier. So I've got 2/4 minus 9/4. Well, 2 minus 9 is -7. So I've got -7/4 radical 7 plus, can't reduce this any further, 10/3 radical 2. Okay, that's one way to write this answer. This is sufficient. It's good. I just want to show you another way that you might see something like this, because again, multiplication and division kind of go together. Right now, it kind of says do 7 divided by 4, then multiply by radical 7. Okay, it's actually the same as doing this. I could do 7 times radical 7 and then divide by 4. I get the same answer. Same with this term over here. Right now it says do 10 divided by 3 and then multiply by radical 2. But that's actually the exact same as doing 10 radical 2 over 3. Okay? These are the exact same values, exact same answer, just a different way to write it. You need to be familiar with both. Okay, we've done some simplifying of radicals. We have added and subtracted. Now we're going through a set of multiplication dealing with radicals. Now, again, let's take a look at this. You have 2 radical 3 and 3 radical 6. So the 2 radical 3 is obviously joined by multiplication. The 3 radical 6 is obviously joined by multiplication. But what is in between the 2 brackets? Also multiplication. Okay, so again, the radical 6 looks like it's more connected to the number 3, but it's not. These guys can be multiplied any which way we like. Do you remember what that property is called? Okay, that's the commutative property of multiplication, or commutative, however you say it. I don't really care. I call it commutative property. Okay, what does that allow us to do? Well, it allows us to multiply our whole values together, and it allows us to multiply our radicals together. So I'm actually going to rearrange this multiplication here, and we're going to put our whole numbers together. 2 times 3. And I'm going to put my radicals together. Radical 3 times radical 6. Now again, the multiplication sign needs to be between the 2 and the 3, otherwise it would look like 23. But the whole bracketing and putting the multiplication sign here is pretty arbitrary. I could just write radical 3, radical 6, or I could write 2 times 3, radical 6, and it would mean the exact same thing. Okay, I'm just doing this so that we can see pretty easily that I'm trying to group my whole numbers, which is 6, and group my radicals. Now it looks like these guys are simplified as far as they could be. And if they were by themselves, that would be true. But I can use my multiplying radicals rule kind of in reverse as to how we've used it before. And I can actually rewrite this as radical 3 times radical 6. Now that looks like going backwards. But I end up with radical 18. And radical 18 can be simplified using a square number. Okay, radical 18 is the same as radical 9 times 2, which gives me 6 times radical 9, radical 2. Radical 9 is 3. 3 times 6 is 18. 18 radical 2. So this is an example of a situation where it kind of looks like you're done up here, or maybe done here, but actually you can keep going. You can put these radicals together, create a new radical, which can be simplified further, and then this is the final simplified answer. As long as your radical is as, in lowest terms, I guess you could say, is as simplified as possible, then you've done a good job, okay? Let's look at our next one. We have a similar situation. We're going to apply another property that's common to algebra. This time we have 2 times radical 3. And then that's being multiplied by this group, but the group itself is separated by addition. So which property do we need here? Give you a hint, search the D. Distributive property. Well, what does the distributive property say? Well, it says that this factor needs to be multiplied by that factor, and by that term, by this term, and by this term. This guy in the brackets here is a binomial. Alrighty then, let's carry on. 2 times radical 3 times 4. Remember, commutative property. 2 times 4, radical 3. 2 times 4 is 8. Radical 3. Don't forget this part. Good. Next, plus 2 times 5 is 10. Radical 3 times radical 3, it's actually going to end up being 3, but we'll do it in 2 steps. 2 times 5 is 10. Radical 3 times radical 3 is radical 9. 8 radical 3 here. Radical 9 is 3. Square root of 9 is 3. Times 10 is 30. And this guy's done. I can't add these together any other way because I've got a radical here and no radical here. And you can only add like radicals. So this one is done. So there's 2 quick examples. Commutative property being used all the time. Distributive property can also be used with radicals, just like if this was, 4 plus x or something like that. There's nothing really new in this example, but just being careful with your adding and multiplying of radicals, looking for those patterns, looking for those square numbers. And so I'm going to do it fairly quickly, but you should always be trying to think ahead of me so that by the time I do it, you've already thought through it. And then when I do it, it's just kind of confirming your answer or correcting your strategy. But don't just sit there and wait for me to do it and then copy it down and think that you've learned something. That's not learning. Think ahead of me. Think of what we're going to be doing here. Right away, you should see, in this case, we're going to be using the distributive property. So I've got my outside monomial times the first term in the binomial and times the second term in the binomial. And let's see what that looks like. Okay, negative 7 times 6 is negative 42. Radical 2 times radical 8 is radical 16. That's going to be nice. Then I have negative 7 times negative 11. Negative times negative is a positive. That's going to be 77 radical 2. This is going to be negative 42. The square root of 16 is just 4. plus 77 radical 2. For this one, I'd probably break out my calculator, but for the sake of speed, I'll do it in my head. 168 plus 77 radical 2. That's as simplified as that one's going to get. All right, again, in D, we have distributive property. This time, I have a binomial in both brackets, so this is a FOIL situation, right? First times first, outside times outside, inside times inside, last times last. Another way to think about that, again, is just writing the word FOIL and then taking care of all those pieces. We should end up with 4 terms. We're going to do first times first, outside times outside, inside times inside, last times last. Here we go. First times first. Radical 3 times 2. Well, that's 2 radical 3. Okay? Positive. Then we have outside times outside. Radical 3 times negative radical 3. Okay? I'm going to just write that step down, but we've got radical 3 times negative radical 3. Then we have inside times inside. That's 5 times 2. Again, I'm writing down all of the pieces and then I'll simplify it. I wouldn't do this if it was my homework. I'd skip to the next step, but last times last is 5 radical 3 and it's negative, okay? Negative 5 radical 3. Simplifying. I see some like terms that I could group right away. I'm going to go ahead and simplify the in-between pieces first, okay? 2 radical 3. This is a positive times a negative, so it's negative, and it's radical 3 times radical 3, which is radical 9, which is 3. Okay? Another way to say that is, look, you're taking the square root of 3, multiplying it by the square root of 3. Well, the square root of 3 is a number times itself is 3. Well, if I times it by itself, it's going to be 3. Okay. Now you got 5 times 2 is 10 minus 5 radical 3. Again, if I were doing this in my practice problems, I would go straight from the problem to this step. Okay. And now I can group my like terms. I've got some whole numbers here in the middle. 10 and negative 3. That's going to be positive 7. And then I have radical 3's. I've got 2 of them here and negative 5 of them there. That's going to be minus 3 radical 3. You might have put this the other way. You might have written this, let's just put a little or. If you had this term first, you just need to make sure that your negative signs go together. So if you wanted to keep your radicals first, you'd have 2 minus 5, that's negative 3 radical 3. And then you'd have negative 3 plus 10 is plus 7. Okay, these guys are exactly the same. 3E looks pretty scary. You might automatically think, oh, I know what to do. Distributive property, I'm going to FOIL this. First times first, outside times outside, inside times inside, last times last. But you should notice something else about this. Look at this term here. Call it A. It's the same as this term here. Let's call it A. Look at this term here, 3 radical 3. Let's call it B. And this term here, 3 radical 3. Let's call it B. So what we actually have here is A plus B times A minus B, which is the product, right? Multiplication is a product. It's the product of a sum and a difference. Do you remember that? The product of a sum and a difference. The product of a sum and a difference can be reduced to or reduced by or simplified by. It's the same as a difference of squares. Okay? Did you sneak it in there before me? Product of a sum and difference is the same as a difference of squares. That means a squared minus b squared. Okay? That makes this problem really easy because all I need to do now is fit the pattern with what I've been given. Well, 2 radical 2 is a. So my pattern of going from a product of a sum and a difference to a difference of squares tells me that all I have here then is 2 radical 2 squared. And I'm going to subtract b squared. Well, b is 3 radical 3 squared. Now you might say, well, that looks smaller, but it certainly doesn't look any less complicated. But if we know our laws of exponents, then this becomes pretty straightforward. if I have two factors in a bracket, I have to remember that both of them get squared. Okay, just quick review, you don't need to write this, but if I had, let's say, 2x, and I put that in brackets, I have to remember that this is 2 squared times x squared, which is 4x squared. Both pieces get squared. Okay, that's different than this. In this situation, the exponent only belongs to the variable. In this situation, the exponent belongs to both pieces, okay? That's just to help us understand that here we actually have 2 squared times the square root of 2 squared. Okay, well, 2 squared is pretty easy. It's 4. But the square root of 2 squared is also easy. If I square root and square something, those are inverse operations. I'm just going to be left with the value in the radicand. Okay, I'm going to be left with 2. Because if I take the square root of 2 and I multiply it by itself, I'm going to get 2. Because the square root, a square is a number multiplied by itself. Okay, here we go. So 2 squared is 4. Square root of 2 squared is 2. Over here we have 3 squared, that's 9. And the radical 3 squared is 3. It's itself. 4 times 2 is 8. 9 times 3 is 27. 8 minus 27 is negative 19. Example 4 is our token word problem. One in every lesson, I suppose. And we're given a pyramid. It says a square-based pyramid. That's key, square base. Has a height of 9 centimeters. The volume is given. It's 1,089 cubic centimeters. And we need to find the exact side length of the square base. Well, what do we know? What do we need to know? We're going to need a formula for the volume of a pyramid, and we're going to need a variable to represent the side length x of this square-based pyramid. So we're going to let x be side length of the base. We're going to let x be the side length of the base, and then we also need a formula for the volume of a pyramid. The volume of the pyramid is, and I'm giving this to you, it's 1/3 times the area of the base, times the height of the pyramid. All right, here we go. Subbing in what we know. We're given the volume, 1,089 equals 1/3 times the area of the base. The area of the base we don't know, but we did let x be the side length of the base. So the area of the base then is x times x, or x squared. I'm going to use a dot there so we don't get it confused. A dot just means multiplication, okay? X squared is the area of the base, and we are given the height is 9. All right, well, let's work on simplifying this. My right side I can simplify. I'm going to leave the left side as 1,089. 1/3 of 9, or 1/3 times 9 is 3. So I've got 3x squared on the right. Now I'm trying to simplify, I'm trying to reduce, I'm trying to get the value of x. I want to isolate x. So again, I'm thinking bed mass, but this time I'm thinking in reverse because I'm stripping things away from my variable x. There is no addition and subtraction to deal with. There's multiplication and division though. And then I'm going to deal with this exponent. Okay? So we're going to divide both sides by 3. What does that look like? Divide this side by 3 means I have to divide that side by 3. I divide this side by 3 in order to get x squared by itself. Okay. And over here, 1,089 divided by 3 is, calculator, click, 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 363. And now, I'm not going to use my calculator because the problem asks me for the exact side length. And if I just take the square root of 363, I'm actually going to get a decimal, and I don't want that. So I'm going to apply what I know about radicals. I'm going to take the square root of both sides. Okay, so and I'm also going to switch these sides around, but this one's easy. The square root of x squared, right? X is being squared and square rooted, inverse operations. I'm just going to be left with x. If I do something to x and then I undo it, I'm just going to have x. Okay, good. X is equal to the square root of 363. Again, if I take the square root of 363 in my calculator, I'm going to get a decimal. Another thing to note here is that the square root of a positive value could be positive or negative, right? So there is a number, a, that if I multiply it by itself, it equals 363. Okay, this might be a decimal number or irrational number, whatever, it doesn't matter. There is a number that if I multiply it by itself, I'll get 363. But what's also true is if I took negative a times negative a, I could also get 363. Now, in our situation where we're talking about side lengths, okay, I'm not going to worry about the negatives because I can't have a negative side length. It doesn't make any sense. So I'm only dealing with the positive square root, this positive radical, okay? So let's go. We've got 363. If you're good with your square numbers, you know that this is divisible by 121, which is 11 squared, or which square root of 121 is 11. So I'm going to go ahead and write that on the right-hand side, that this number can be broken into 121 times 3. That's going to give me 11 radical 3. And I'm done. Okay. That means the length of each side of the square base for this pyramid is 11 radical 3. It's just a number, okay? It's an awkward number. It's a mixed radical, but it is a number and it is an exact number. If you want to see why we do this, go ahead and punch that into your calculator. Radical 3 times 11, or 1 radical 3, and hit enter, and you'll see you get an awkward decimal that is not exact. It's rounded, as we discussed earlier. So the exact side length of base is 11 radical 3. And what units are we working in? Centimeters. All right, folks. Your practice problems for this lesson are found on page 39. And you're responsible to know all of the information covered by numbers 1 through 9 and 16.